Hi everyone. We're going to talk today about binomial distributions and specifically how to find the mean and standard deviation of a binomial distribution. So let's set forth some variables that we're going to need. Of course, little p represents the probability of success in a binomial distribution. 1 minus p then is the probability of failure. Oftentimes in some textbooks, you will see this probability of failure simply noted as Q instead. So if we have a random variable x that we know to have a binomial distribution based on n observations with probability of success p, then the way in which we find the mean of that random variable x, so mu sub x, is by taking the number of observations n and multiplying it by the probability of success p. The standard deviation then of the random variable x we find by doing the square root of n times p times 1 minus p. Since q is often used to represent that probability of failure, you sometimes might see this done as the square root of n times p times q. Now, one big thing to remember though is these rules are only for a binomial distribution. When you move into other distributions, you'll have different rules. So let's take a look at a couple problems. Each of these are going to be from the Practice of Statistics textbook, 3rd edition. And the first one we're going to look at is number 8.22. So back in 1998, Mark McGwire of the St. Louis Cardinals hit 70 home runs, which was, at the time, the new major league record. So the question is, if this feat was as surprising as most of us thought at the time. In the 3 seasons leading up to 1998, McGwire hit a home run in 11.6% of his times at bat. He went to bat 509 times in 1998. McGwire's home run count in 509 times at bat has approximately the binomial distribution with n, the number of observations, as 509, and little p, the probability of success, is 0.116. That comes from the 11.6% times that he hit a home run. So what is the mean number of home runs he would hit in 509 times at bat? So the first thing we'd have to do is set forth our random variable. So let's let our random variable x be the number of home runs that he hits. So if we want the mean number that he would hit out of 509 times at bat, n is 509, and all we do is simply multiply that by the probability of success. So if you multiply those together, because this is n and this is p, you get 59.044. All right, so think about what that tells us. So he went to bat 509 times. What mu sub x really tells us is how many home runs we would have expected out of those 509 times at bat. Remember that when we're talking means of random variables, they're often referred to as an expected value. So instead of straight out asking us for the mean number he would have hit, what they could have asked us was how many home runs might we have expected out of Mark McGwire's 509 times at bat. So out of those 509 times, we would have expected 59. Well, he hit 70. So yeah, that was pretty a big deal. Much, much higher than what we would have expected. So let's look at another problem. So many local polls of public opinion often use sample sizes of 400 to 800 people. So consider a poll of 400 adults in Richmond, Virginia, that asks the question, do you approve of President Bush's response to the World Trade Center terrorist attacks in September 2001? Suppose that we know that Bush's approval rating on this issue nationally was 92% a week after the 9/11 incident. So this question is going to have three different parts. So the first part is asking us to identify the random variable x and determine if that random variable is binomial. So in establishing what the random variable is, it sounds like we're trying to figure out what his approval rating was. So let's x be, I guess, just the approval. Of Bush's response So if we want to determine if it's binomial, remember that there's 4 criteria that need to be met in order for a distribution to be binomial. First of all, there must be identified a success and a failure. Well, success, I guess, could be identified as approving of Bush's response. If a person approves or is approving of his response. And that means a failure, of course, is then not approving, does not approve. Right? The second criteria is that there needs to be a fixed number of observations or trials. Now in this case, there was a fixed number of people that were asked the question. That was how many people were polled. So in this case, our fixed number is that n equals 400. The third criteria is that those observations, those trials, need to be independent of one another. Well, if we're asking 400 people this question, it should be the case that whether or not one person approves is independent of another person approving. And finally, the fourth criteria is that there does need to be a designated probability of success. Well, the best thing we have to go for in this case is what his approval rating was a week after the 9/11 attacks. And so we can use that for our probability of success. He had a 92% approval rating. So it does appear that the random variable that we have identified here is indeed a binomial distribution. So let's do some calculations now. So the second question, calculate the binomial probability that at most 358 of the 400 adults in the Richmond poll answered yes to the question. So let's lay out first what that probability is we're trying to find. We're trying to find the probability that x is going to be at less than or equal to 358 because we want at most 358. So if you think about what this means, especially in terms of that formula that you might remember for a binomial distribution probability, we'd have to figure out the probability that x equals 1 plus the probability x equals 2 plus the probability x equals 3 all the way up to 358. Well, there's a much easier way, of course. We can use our graphing calculators to do this. So let's switch over to that. Remember, if you go under second vars and scroll down, we're looking for binom CDF. Remember, that stands for binomial continuous distribution function. The continuous distribution functions are always the less than or equal to probabilities, as I like to think of them. So let's bring that one up. So we had 400 trials, because that's how many people we asked. Our probability of success was 0.92. And we want to see 358 people at most approving of how Bush handled the 9/11 attacks. Now, if by chance you have an older calculator, like a TI-83 for instance, remember you need to type the values in those parentheses, and what you see here on the screen is the order in which you'll be typing them in. All right, it's always n first, followed by p, followed by the x value that you want to see. So that gives us an answer of 0.044 about. So if you think about what that means is, expressing this as a decimal, like a percent, that would be 4.4%. So the chances that at most, like no more than 358 people agreed with how Bush handled all this was 4.4%. So let's look at the last one. So now we're asked to determine the expected number of people in the sample who would indicate approval, and then find the standard deviation of that random variable x. All right, well, there's that phrase again, expected number. And remember, that's how you'll often see it expressed when really what they want you to find is the mean of the random variable. All right, so remember how the formula goes, simply n times p. So out of 400, our probability of success is 92. So if we multiply those together, that's 368 people. Which, I don't know, I think it makes sense. We have 400 people we asked. We know that Bush's approval rating at the time was 92%, so you're taking 92% of 400. That's how we figure out how many we would expect to agree with that, the way in which Bush handled everything. Now the standard deviation then, remember that was the other formula we looked at. That's the square root of n times p, and I'm just going to use q, okay, for that probability of success. Remember, q though is really just 1 minus p, okay? So we have square root, big square root, 400 times p, which is 0.92. That makes, of course, q, our probability of failure, 0.08. So if you go ahead and number crunch that gives us a standard deviation of about 5.426 about. So overall, when you're finding means and standard deviation of binomial distributions, not too difficult. You really just need to know the rules. Doing the probabilities as we did here in B, that's often a big question that you're asked. But hopefully this lesson helps you focus a little bit more on some of those other characteristics and values that you can find in regard to a binomial distribution.